Okay, so as we can see, this normal distribution can be really useful in a sense that according to the central limit theorem, when you're taking either a summation of random variables or you're taking the average of a bunch of random variables, the resulting distribution of the summation or the average, this guy or this guy, will both have a nice random distribution that can be easily handled. The normal distribution right here, and right here. Now remember, this is obtained regardless of what distribution xi's have. All the x's only need to be independent. They can follow any distribution they want. So we have relatively general conditions and obtain eventually a very nice result saying you don't have to consider anything else as long as you're taking the summation or average, and as long as you're taking the summation or the average of sufficiently large number of random variables, you only need to do normal distribution calculation, as we have seen here. This is a very important property. This is actually the bridge between probability theory, because we're talking about random variables here, and statistics, because statistics is about taking average, and in here you are looking directly at an average calculation. In the next chapter, we'll start our story based on what you are seeing here, and we'll use a number of discussions surrounding the central limit theorem and also surrounding normal distribution. Okay. Now, because of the central limit theorem and because this normal distribution is so powerful to represent summation or average, it can actually be used to represent or to approximate some of the distribution we discussed earlier. Remember binomial distribution? Binomial distribution is what? Binomial distribution is counting the total number of success in n tosses, in 100 tosses, in 200 tosses. Okay. So if you are looking at each toss or each trial as one random variable x1, x2, x3, and you use 1 and 0 to represent success and failure, then when you sum up all these 1s and 0s, when you do the summation of these 1s and 0s, it actually will be equal to the total number of success, right? If you use 1 as success and 0 as failure, when you add up these 1s and 0s, you have the success. And this is our binomial distribution. Or in other words, this binomial distribution is actually a summation of random variables. And in that case, as we have seen earlier, it's possible to use normal distribution to approximate binomial distribution. Similarly, remember Poisson distribution? In Poisson distribution, you're also counting the number of successes, but it's in the relatively continuous range. But no matter if you're looking at continuous or discrete, you're still counting the number of success. This is still a summation. And since it's a summation of random variables, you can still approximate it using normal distribution. Okay? Easy one. So to do the approximation of both, we'll do it one by one. Let's say if I binomial run the variable x. If it follows, let's say, a binomial distribution with n, parameter n and p, so this will be your number of tosses and the success rate or success probability. Now in the textbook or some simple calculation, we know the mean of x will be np. The number of tosses multiplied by the success probability will give you on average how many successes you should see. The variance of x will be equal to np 1 minus p. Now the approximation said the following. If you introduce another random variable, let's say x hat, follows normal distribution with mean np and variance np 1 minus p, then the probability that x less than a certain number a is approximately equal to the probability that the random variable x hat is less than the same number. This is the binomial approximation using normal distribution. For Poisson distribution, the same idea. Poisson distribution is only defined by one parameters, lambda. And as we know, lambda is the average number of success for a Poisson random variable, and as a matter of fact, lambda is also the variance of a Poisson random variable. So if you want to define a normal random variable approximated, apparently use the same mean, the same variance, and it's not difficult to find out by calculations or by using computers that this relationship will happen for almost all a's within the physical range. Now, since Poisson distribution and binomial distributions are discrete random variables, there will be a little trick in constructing this approximating normal distribution. Okay. So this hat in the selection of the parameters may be a little tricky, especially for binomial distributions. If you're interested, you can look at section 3.5 of the textbook, which explains how these approximations can be used. And in our class on Tuesday next week, I will use the Minitab to illustrate how the distributions can be visualized so that you can see how the two are actually very similar to each other. Okay. But for now, we'll end the lecture videos, and you can view them and